Beneath the world we know lies a silence we cannot touch. A table feels solid. A star burns with steady fire. The moon arcs predictably across the sky. Reality, to our senses, seems continuous, stable, familiar. But this surface is only a mask, a thin veil stretched across an abyss of uncertainty. Pull it back, and the universe dissolves into strangeness. Here, particles do not have fixed positions, only probabilities. Light behaves as both wave and particle, as if undecided. Forces emerge from invisible fields that ripple and fluctuate even in emptiness. An entanglement weaves threads of connection so deep that distance itself seems meaningless. This is the quantum veil, a hidden tapestry beneath the fabric of reality, where every rule bends, every certainty breaks, and every intuition falters. The quantum world is not another place, tucked far away. It is here, beneath every stone and every breath. It is the heartbeat of matter, the flicker of energy, the logic by which stars ignite and atoms endure. And yet, it is alien to our minds. It defies our language, mocks our expectations, resists our need for clarity. For to look beneath the veil is to confront a truth that may not be knowable in the way we desire. That the universe is not deterministic, but probabilistic. Not fixed, but fluid. Not solid, but spectral. And so we are left with the question that drives physics, philosophy, and imagination alike. What lies beneath the quantum veil? Is it chaos or hidden order? An infinity of branching worlds or a single thread of deeper law? Does it conceal the birth of reality itself or the boundary of our understanding? Tonight, we journey into that hidden world where light becomes paradox, emptiness becomes fullness, and reality itself trembles on the edge of the unknown. The fall of certainty, cracks in the clockwork universe, the dream of a perfect machine. For centuries, the universe was imagined as a flawless clockwork. In the vision shaped by Isaac Newton, every planet followed a calculable orbit. Every falling apple obeyed a precise equation. Space was absolute. Time was universal. And forces acted across the void with perfect predictability. It was a cosmos of certainty. If one knew the position and motion of every particle at one moment, Newton's laws promised the future could be foretold with absolute precision. Pierre-Simon Laplace captured this dream most starkly. He imagined a vast intelligence, later called Laplace's demon, that, knowing every atom's place and momentum, could predict every event, past and future, in perfect detail. Here, the veil did not exist. Reality was transparent, a grand design without secrets. The universe was not mystery, but mathematics. But cracks soon appeared in this shining edifice. The flicker of fire, blackbody radiation. The 19th century was an age of mastery. Industrial revolutions roared, steam engines thundered, and physicists declared the laws of thermodynamics complete. Yet even then, fire betrayed them. When scientists studied the spectrum of light emitted by a heated object, a black body, classical physics failed. According to Newtonian expectations, the radiation at short wavelengths should climb without bound, producing infinite energy in the ultraviolet. But this was absurd. Real objects glowed red, then white, but never infinite. This failure became known as the ultraviolet catastrophe. The clockwork was cracking. The universe, it seemed, refused to follow the script. In 1900, Max Planck proposed a desperate fix. He imagined that light was not continuous, but emitted in discrete packets, quanta of energy proportional to their frequency. He did not know why this worked, But the catastrophe was averted. For the first time, physics whispered that beneath the smooth veil of classical law lay something granular, strange, unseen: Einstein's light quanta. Planck's solution was radical but modest. He hoped quanta were a mathematical trick, not a real feature of nature. But in 1905, Albert Einstein took the next step, investigating the photoelectric effect, where light shining on a metal ejects electrons. Einstein showed that light must be made of real particles, which he called quanta, later named photons. Only photons with energy above a threshold could free electrons, no matter how intense the light. Light, the most perfect of waves, was also a particle. Duality had crept beneath the veil. Certainty trembled. The atom's spectral secrets. The mysteries deepened with atoms themselves. Hydrogen, the simplest atom, emitted light at specific colors, not a continuous spectrum. These sharp lines made no sense in a Newtonian universe. Why should electrons radiate at some energies but not others? Why did atoms not collapse as electrons spiraled into nuclei, losing energy with each orbit? Classical physics could not answer. Atoms should not even exist. The very solidity of matter was a paradox. In 1913, Niels Bohr proposed that electrons orbited nuclei in quantized shells, jumping between levels and emitting photons of precise energies. His model explained hydrogen's lines, but raised deeper questions. What force allowed such forbidden jumps? What strange rule dictated that only certain orbits were allowed? The veil thickened. Heisenberg's challenge to certainty. The cracks widened into fissures. Werner Heisenberg, working in 1925, realized that electrons could not be pictured as tiny planets orbiting nuclei. Instead, they must be described only by probabilities, their positions and momenta never simultaneously knowable. His uncertainty principle shattered Laplace's dream. At the quantum level, prediction gave way to probability. The veil was no longer just a mathematical tool. It was reality itself. Beneath appearances, the universe refused to reveal both where things were and how fast they moved. Certainty had died. Schrödinger's waves and the cat in the box. In 1926, Erwin Schrödinger unveiled his wave equation, treating particles as waves of probability. Electrons became standing waves around nuclei, forming orbitals instead of orbits. The atom, once a miniature solar system, became a shimmering cloud. But Schrödinger recoiled at his own creation. To expose its strangeness, he imagined a cat sealed in a box, linked to a quantum event. Until observed, the cat would be both alive and dead, suspended in a ghostly superposition. The veil, it seemed, blurred even the line between life and death. Einstein's resistance. Einstein, though father of the photon, could not accept this loss of certainty. God does not play dice, he insisted, arguing that quantum theory must be incomplete, that hidden variables must lurk beneath the veil, restoring order. But experiments decades later, guided by John Bell's theorem and confirmed by Alan Aspect, proved Einstein wrong. The veil did not conceal deterministic laws. It revealed entanglement, a non-local strangeness beyond any classical order, the end of certainty. By the mid-20th century, Newton's clockwork was broken. The universe was no longer transparent, but veiled, its rules probabilistic, its nature dual, its boundaries uncertain. The fall of certainty was not a failure of science, but a transformation of it. Physics had pulled back the veil and found not order, but mystery. The world above still felt solid, predictable, dependable. But beneath, in the quantum realm, reality itself shimmered like a mirage, stable only when measured, dissolving into probability when left unseen. The fall of certainty marked the beginning of a new cosmos, one stranger, deeper, and more unsettling than any before. A universe where the veil was no longer an illusion, but the most fundamental truth. Heisenberg's shadow, the uncertainty of reality, the shattered dream. By the early 20th century, physics was adrift in strangeness. Planck's quanta and Einstein's photons had already unsettled Newton's clockwork universe. Bohr's quantized atom had explained hydrogen's spectrum, but at the cost of replacing orbits with mysterious jumps. Beneath the visible world, the laws of certainty were fraying. Into this tension stepped a young physicist with a restless mind, Werner Heisenberg. In 1925, while struggling with the behavior of electrons, Heisenberg realized something profound. The failure was not in the mathematics, nor in the measurement techniques. The failure was in reality itself. The universe, at its deepest level, refused to reveal its full truth, the uncertainty principle. Heisenberg's insight crystallized into a law that would redefine reality, the uncertainty principle. It declared that certain pairs of properties, position and momentum, energy and time, could not be known with unlimited precision. The more clearly one property was measured, the less clearly the other could be defined. This was not a statement about technological limits. It was not a flaw in microscopes or detectors. It was a law of nature. Electrons did not have precise positions and momenta simultaneously. They existed as clouds of probability, shimmering possibilities until disturbed by observation. The veil of reality had thickened into a permanent fog, the death of determinism. In classical physics, the present dictated the future. If you knew where something was and how fast it was moving, you could predict its path indefinitely. The uncertainty principle shattered that dream. The future was not written, only probable. Einstein rebelled. God does not play dice, he argued, unwilling to accept randomness at the foundation of reality. But dice were indeed being thrown. Probability, not certainty, governed the quantum world. Laplace's demon, the all-knowing intelligence of Newtonian fantasy, was dead. The veil could not be lifted, not because our eyes were weak, but because nature itself was veiled. Bohr's Copenhagen interpretation. Niels Bohr, Heisenberg's mentor, sought to make sense of this. In what became known as the Copenhagen interpretation, Bohr proposed that quantum systems do not have definite properties until they are measured. Before observation, an electron is not here or there, but both, a superposition of possibilities. Reality, in this vision, is not fixed. It is participatory. The act of measurement forces the veil to part, collapsing possibilities into a single outcome. The observer and the observed are inseparable. This was not determinism. It was not randomness in the classical sense. It was something stranger, a reality that is only half formed until looked upon. The paradox of the cat. To illustrate the absurdity, Erwin Schrödinger crafted a thought experiment in 1935. Place a cat in a sealed box, linked to a quantum event. Say, the decay of a radioactive atom. If the atom decays, poison is released, and the cat dies. If not, the cat lives. Quantum mechanics insists that until the box is opened, the atom is both decayed and not decayed, the cat both alive and dead. Only observation collapses the veil. Schrödinger intended this as a critique, a reductio ad absurdum. Yet the paradox captured the heart of the mystery. The veil of quantum mechanics did not end at the scale of atoms. It extended upward into life itself, mocking the line between possibility and actuality. Einstein's rebellion. Einstein remained the great skeptic. He argued that quantum mechanics was incomplete, that hidden variables must exist beneath the veil, restoring determinism. He debated fiercely with Bohr, their arguments echoing across conferences and letters. In 1935, Einstein, Podolsky, and Rosen published a paper presenting the EPR paradox, arguing that quantum mechanics was flawed. They showed that entangled particles, separated by vast distances, seem to affect each other instantaneously. Spooky action at a distance. For Einstein, this was proof that something was missing. Bohr disagreed. He insisted that entanglement was not a flaw, but a feature. Reality, he argued, was holistic, not separable. The veil was not local. It was woven across space itself, the shadow of mystery. For decades, the uncertainty principle and the Copenhagen interpretation stood untested, more philosophy than physics. But as quantum mechanics proved spectacularly accurate in experiments, its paradoxes could not be dismissed. Lasers, semiconductors, nuclear energy, magnetic resonance imaging, all emerged from equations rooted in uncertainty. The veil was strange, but it was powerful. It shaped not only atoms, but the modern world. And yet the shadow remained. Was uncertainty the true nature of reality, or a symptom of incomplete knowledge? Was the veil permanent, or could deeper laws restore clarity? The emotional weight of uncertainty. Beyond equations, the uncertainty principle carries a philosophical weight unlike any other. It tells us that the universe is not fully knowable, that there are questions with no answers, not because we have not found them, but because they do not exist to be found. For humanity, accustomed to clarity, this is unsettling. For centuries, we believed the cosmos was transparent, awaiting our discovery. Heisenberg showed that beneath appearances lies ambiguity. Reality itself is shadowed, veiled, unreachable in its fullness. But perhaps uncertainty is not failure. Perhaps it is invitation. The veil is not a wall, but a mystery, urging us to wonder, to imagine, to reflect. The veil descends. By the 1930s, physics had crossed a threshold. The classical dream of certainty was gone. In its place was a universe where probability ruled, where observation shaped reality, where the veil was as real as the world it concealed. This was not the end of science. It was its transformation. For in embracing uncertainty, physics opened the path to deeper mysteries, entanglement, fields, and the very structure of space-time. Heisenberg's shadow still falls across the quantum world. It is the reminder that beneath every answer lies ambiguity. Beneath every clarity lies fog. The veil cannot be torn away. It can only be approached, respected, and wondered at. Entanglement, threads across the veil, the phantom connection. In 1935, Albert Einstein leveled his sharpest critique at quantum theory. Along with Boris Podolsky and Nathan Rosen, he argued that if quantum mechanics was correct, then particles could share a connection so strange it defied space itself. Measure one particle here, and its twin, light years away, would instantly reveal the opposite result. To Einstein, this was impossible. Spooky action at a distance, he called it, a phrase that still lingers like an echo of disbelief. Bohr's quantized atom had explained hydrogen's spectrum, but at the cost of replacing orbits with mysterious jumps. Beneath the visible world, the laws of certainty were fraying. Into this tension stepped a young physicist with a restless mind, Werner Heisenberg. In 1925, while struggling with the behavior of electrons, Heisenberg realized something profound. The failure was not in the mathematics, nor in the measurement techniques. The failure was in reality itself. The universe, at its deepest level, refused to reveal its full truth. The uncertainty principle. Heisenberg's insight crystallized into a law that would redefine reality, the uncertainty principle. It declared that certain pairs of properties, position and momentum, energy and time, could not be known with unlimited precision. The more clearly one property was measured, the less clearly the other could be defined. This was not a statement about technological limits. It was not a flaw in microscopes or detectors. It was a law of nature. Electrons did not have precise positions and momenta simultaneously. They existed as clouds of probability, shimmering possibilities until disturbed by observation. The veil of reality had thickened into a permanent fog, the death of determinism. In classical physics, the present dictated the future. If you knew where something was and how fast it was moving, you could predict its path indefinitely. The uncertainty principle shattered that dream. The future was not written, only probable. Einstein rebelled. God does not play dice, he argued, unwilling to accept randomness at the foundation of reality. But dice were indeed being thrown. Probability, not certainty, governed the quantum world. Laplace's demon, the all-knowing intelligence of Newtonian fantasy, was dead. The veil could not be lifted, not because our eyes were weak, but because nature itself was veiled. Bohr's Copenhagen interpretation. Niels Bohr, Heisenberg's mentor, sought to make sense of this. In what became known as the Copenhagen interpretation, Bohr proposed that quantum systems do not have definite properties until they are measured. Before observation, an electron is not here or there, but both, a superposition of possibilities. Reality, in this vision, is not fixed. It is participatory. The act of measurement forces the veil to part, collapsing possibilities into a single outcome. The observer and the observed are inseparable. This was not determinism. It was not randomness in the classical sense. It was something stranger, a reality that is only half formed until looked upon. The paradox of the cat. To illustrate the absurdity, Erwin Schrödinger crafted a thought experiment in 1935. Place a cat in a sealed box, linked to a quantum event. Say, the decay of a radioactive atom. If the atom decays, poison is released, and the cat dies. If not, the cat lives. Quantum mechanics insists that until the box is opened, the atom is both decayed and not decayed, the cat both alive and dead. Only observation collapses the veil. Schrödinger intended this as a critique, a reductio ad absurdum. Yet the paradox captured the heart of the mystery. The veil of quantum mechanics did not end at the scale of atoms. It extended upward into life itself, mocking the line between possibility and actuality. Einstein's rebellion. Einstein remained the great skeptic. He argued that quantum mechanics was incomplete, that hidden variables must exist beneath the veil, restoring determinism. He debated fiercely with Bohr, their arguments echoing across conferences and letters. In 1935, Einstein, Podolsky, and Rosen published a paper presenting the EPR paradox, arguing that quantum mechanics was flawed. They showed that entangled particles, separated by vast distances, seem to affect each other instantaneous, spooky action at a distance. For Einstein, this was proof that something was missing. Bohr disagreed. He insisted that entanglement was not a flaw, but a feature. Reality, he argued, was holistic, not separable. The veil was not local. It was woven across space itself, the shadow of mystery. For decades, the uncertainty principle and the Copenhagen interpretation stood untested, more philosophy than physics. But as quantum mechanics proved spectacularly accurate in experiments, its paradoxes could not be dismissed. Lasers, semiconductors, nuclear energy, magnetic resonance imaging, all emerged from equations rooted in uncertainty. The veil was strange, but it was powerful. It shaped not only atoms, but the modern world, and yet the shadow remained. Was uncertainty the true nature of reality, or a symptom of incomplete knowledge? Was the veil permanent, or could deeper laws restore clarity? The emotional weight of uncertainty. Beyond equations, the uncertainty principle carries a philosophical weight unlike any other. It tells us that the universe is not fully knowable, that there are questions with no answers, not because we have not found them, but because they do not exist to be found. For humanity, accustomed to clarity, this is unsettling. For centuries, we believed the cosmos was transparent, awaiting our discovery. Heisenberg showed that beneath appearances lies ambiguity. Reality itself is shadowed, veiled, unreachable in its fullness. But perhaps uncertainty is not failure. Perhaps it is invitation. The veil is not a wall, but a mystery, urging us to wonder, to imagine, to reflect. The veil descends. By the 1930s, physics had crossed a threshold. The classical dream of certainty was gone. In its place was a universe where probability ruled, where observation shaped reality, where the veil was as real as the world it concealed. This was not the end of science. It was its transformation. For in embracing uncertainty, physics opened the path to deeper mysteries, entanglement, fields, and the very structure of space-time. Heisenberg's shadow still falls across the quantum world. It is the reminder that beneath every answer lies ambiguity. Beneath every clarity lies fog. The veil cannot be torn away. It can only be approached, respected, and wondered at. Entanglement, threads across the veil, the phantom connection. In 1935, Albert Einstein leveled his sharpest critique at quantum theory. Along with Boris Podolsky and Nathan Rosen, he argued that if quantum mechanics was correct, then particles could share a connection so strange it defied space itself. Measure one particle here, and its twin, light, a phrase that still lingers like an echo of disbelief. For him, this was proof that quantum mechanics was incomplete. There had to be hidden variables, deeper laws beneath the veil, that restored locality and causality. Surely the universe would not stitch particles together across empty space. Surely physics would not permit a thread that defied distance. But the universe is stranger than Einstein dared it. The birth of entanglement. Entanglement begins in simplicity. When two particles interact, their quantum states become linked. They are no longer independent, but described by a single wave function, a single mathematical object. Separate them by any distance, and this unity persists. Spin, polarization, momentum. Whatever property they share, it remains correlated. Measure one, and the other knows, instantly, no matter the separation. It is as if the veil itself binds them, weaving invisible threads that stretch across the fabric of space. Entanglement is not rare. It underlies the bonds of atoms, the chemistry of molecules, the stability of matter. Every breath you take, every photon of light, carries with it the silent mark of entanglement. The veil is threaded with it. Bell's theorem, testing the veil. For decades, entanglement remained a philosophical debate. Could it be tested? In 1964, physicist John Bell found a way. He derived a set of inequalities, mathematical limits, on correlations that any local hidden variable theory must obey. If experiments violated Bell's inequalities, then no hidden variables could save classical reality. The veil would be proven real. The tests began in the 1970s, culminating in Alain Aspect's experiments in the 1980s. Pairs of photons were created, their polarizations entangled. Detectors measured them at opposite ends, with settings chosen too quickly for signals to pass between them. The results? The inequalities were violated. The universe, with cold precision, confirmed entanglement. Einstein's dream of hidden order was gone. Spooky action was not a flaw. It was truth. The web of non-locality. Entanglement defies our intuitions about space and time. Information does not travel between particles. Instead, the particles are not truly separate. They are part of one system, stretched across distance. The veil does not separate objects. It binds them. Non-locality does not allow faster-than-light communication. Relativity remains intact, but it reshapes our notion of reality. The world is not composed of independent parts. It is a web, where distance is less fundamental than connection. The power of entanglement. What was once paradox has become technology. Quantum cryptography uses entanglement to guarantee unbreakable codes. Any attempt at eavesdropping destroys the correlations. Quantum teleportation transmits the state of a particle across space, using entangled pairs as bridges. Quantum computers, still in their infancy, rely on entanglement to process information in ways classical machines cannot, solving problems across vast landscapes of possibility simultaneously. The veil is not only mystery, it is resource. Entanglement is not an oddity of the universe. It is its hidden engine. Philosophical reverberations. Entanglement reshapes philosophy as much as physics. If the universe is entangled, individuality is illusion. Objects, particles, beings, none are wholly separate. Reality is relational, not absolute. The veil teaches that connection is deeper than separation, unity deeper than individuality. This resonates with echoes from ancient traditions. The Hindu vision of Indra's net, a cosmic web of jewels reflecting one another endlessly. Or Buddhist notions of interdependence, where nothing exists alone. Science, in its most precise mathematics, rediscovers truths long intuited in myth. The cosmic veil. Entanglement is not confined to particles in laboratories. It may extend across the universe. At the Big Bang, particles emerged from a single wave function. In principle, the entire cosmos may still be entangled with itself, a single fabric of probability woven across all of space. If so, the veil is not local, but cosmic. Every measurement, every observation is a collapse not only of particles, but of the universe itself. Reality is a shared event, unfolding from one entangled whole. Einstein's shadow, revisited. Einstein was wrong to dismiss entanglement, but he was right to sense its strangeness. Spooky action is not comfortable. It challenges causality, locality, even ontology. It is a reminder that beneath the veil, logic bends, categories dissolve, and truth takes a shape our minds resist. Perhaps this is the gift of entanglement. It shows us the limits of our thought. It reminds us that reality is not obliged to fit our intuition. The veil conceals, but in doing so, it reveals the humility of knowledge, threads of wonder. Entanglement is the first true glimpse beneath the veil. It is the evidence that the universe is not separate pieces, but a tapestry woven by invisible thread. It is the revelation that distance is shallow and connection is deep. The veil shimmers with these threads, binding atoms, binding light, binding thought. To pull one is to shake the web entire. Beneath the veil, nothing stands alone. The quantum vacuum, the restless ocean beneath emptiness, the illusion of nothing. At first glance, emptiness seems simple. Strip away all stars, all planets, all dust, even the faintest atoms drifting through interstellar space. And what remains is nothing, a perfect vacuum. For centuries, physicists imagined this void as the baseline of reality, empty, silent, featureless. But beneath the quantum veil, nothingness itself trembles. The vacuum is not empty. It is alive with restless motion, a seething ocean of energy and fluctuation. In the quantum world, even emptiness cannot stay still. Virtual particles, the dance of the void. Quantum mechanics insists that uncertainty governs everything, even nothing. The Heisenberg uncertainty principle states that energy and time cannot both be known with absolute precision. For brief instants, the vacuum can borrow energy, create particles from nothing, and return them before the loan is noticed. These are virtual particles, flickering pairs of matter and antimatter, winking into and out of existence everywhere, all the time. They cannot be directly observed, but their effects are real. They push, they pull, they shape the very structure of space-time. Thus, the vacuum is not empty. It is a storm, a froth, an invisible ocean beneath the veil. The Casimir effect, touching the invisible. In 1948, Hendrik Casimir predicted a strange effect. Place two metal plates very close together in a vacuum, and they will attract each other. Not because of charge, but because the quantum fluctuations between them are restricted. Fewer virtual particles can exist in the gap than outside, creating an imbalance that pushes the plates together. This Casimir effect was later observed in laboratories. Every quantum system has a lowest energy state, called the zero-point energy. Even when cooled to absolute zero, atoms still vibrate, electrons still fluctuate, fields still hum. The vacuum is filled with this irreducible energy, woven into the structure of space itself. In theory, the total zero-point energy of the universe should be infinite. Yet when calculated, it exceeds observed values by 120 orders of magnitude. The most extreme mismatch in physics, known as the cosmological constant problem. This unresolved puzzle suggests that the vacuum may hold secrets far deeper than we grasp. The vacuum and the expansion of the universe. In 1998, astronomers discovered that the expansion of the universe is accelerating. The driver of this acceleration was given a name: dark energy. Its simplest explanation? The energy of the vacuum itself. If the vacuum carries energy, it acts like a pressure, pushing space apart. Unlike matter, which dilutes as the universe expands, vacuum energy remains constant. More space means more vacuum, and thus more energy, accelerating expansion ever further. This transforms the void into the dominant force of the cosmos. Most of the universe is not matter or light, but vacuum. Nothingness is everything. The quantum foam, at scales smaller than atoms, smaller than protons, smaller even than quarks, lies the Planck scale, the smallest meaningful length, where quantum fluctuations of space-time itself become unavoidable. Here, the vacuum may not be smooth but foamy, with space-time bubbling, twisting, birthing tiny black holes and wormholes for instants before collapsing again. This quantum foam, first envisioned by John Wheeler, suggests that emptiness is the most dynamic medium of all. Space is not a stage. It is an actor, restless, shifting, never still. The veil conceals not silence, but storm, Hawking radiation, and the vacuum near horizons. The restless vacuum even shapes black holes. Stephen Hawking showed that near the event horizon, pairs of virtual particles can separate. One falls into the hole, the other escapes, becoming real. The black hole radiates, slowly evaporating over unimaginable timescales. Here, the vacuum writes the destiny of the darkest objects in the cosmos. Emptiness itself gnaws at black holes, erasing even these titans with time. The vacuum as creator. The early universe may have been born from the vacuum. Quantum fluctuations, stretched by inflation, became the seeds of galaxies. Ripples in nothingness grew into stars, clusters, and cosmic webs. The very structure of the visible universe may be the frozen memory of vacuum tremors, amplified to cosmic scales. If so, everything, every sun, every world, every life, is a child of the vacuum. The veil did not conceal creation. It was creation. Philosophical reverberations. What does it mean that emptiness is not empty? That nothingness is fertile, seething with possibility? For philosophy, the quantum vacuum reshapes the oldest questions. Nothing is not nothing. The void is not absence, but potential. Beneath the veil, silence conceals an orchestra of hidden notes, always playing, always becoming. Perhaps the vacuum is not background, but origin. Perhaps existence itself is not built upon something, but upon the restless fertility of nothing. The restless horizon. The quantum vacuum is the most humbling of discoveries. It tells us that reality is not solid, but trembling. That the void is not absence, but energy. That beneath the veil lies not death, but birth. To imagine nothing is to imagine a storm too subtle for our eyes, too vast for our minds. Yet from that storm rises everything we know. Beneath the quantum veil, the deepest truth is not silence. It is restlessness. Many worlds and hidden variables. The splintered reality beneath the veil. The uneasy silence after Copenhagen. By the mid-20th century, quantum mechanics had already proven itself. Its equations worked with uncanny precision. It explained atoms, spectra, chemistry, semiconductors, and nuclear energy. Yet beneath this triumph, unease lingered. The Copenhagen interpretation, Bohr and Heisenberg's vision of wave functions collapsing only upon measurement, had become the mainstream story. But it was not universally accepted. Many physicists treated it less as truth than as a practical rule: shut up and calculate. Still, the philosophical unease remained. Did the veil hide something more concrete? Were particles truly uncertain, or did deeper laws govern them invisibly? Was reality a fog of probabilities, or were we simply blind to its clockwork? Two great answers emerged. One sought hidden clarity. The other embraced infinite multiplicity. Einstein's hope. Hidden variables. Einstein never surrendered to uncertainty. He insisted that quantum mechanics was incomplete. Particles, he believed, had definite positions and momenta at all times. The wave function was not reality, but a shadow of deeper variables we could not yet measure. This vision became known as hidden variable theory. If discovered, These hidden variables would restore determinism, collapsing the veil into clarity. The universe would once again be predictable, governed by laws beneath the uncertainty. But John Bell's theorem in 1964 crushed this hope. His inequalities showed that any hidden variables would have to be non-local, linked across distance, violating Einstein's dream of separability. Experiments confirm this. The veil did not conceal a clockwork. It concealed entanglement. Einstein's ghost lingered, but his vision faded. Everett's rebellion, the many worlds. If the wave function did not collapse, what if it simply continued? In 1957, a young physicist named Hugh Everett proposed the many worlds interpretation. Every time a quantum event occurs, every particle measured, every cat observed, the universe branches. In one branch, the cat lives. In another, it dies. In one branch, you turn left. In another, you turn right. The wave function does not collapse. It multiplies. Reality splits, endlessly, into a growing forest of universes. Everett's idea was radical, dismissed at first as absurd, but it solved a puzzle. No longer did observers cause collapse. The veil was not uncertainty, but proliferation. Everything possible happens somewhere, the forest of universes. In many worlds, the veil conceals not one reality, but infinite reality. Each interaction, each measurement, is a splitting of the cosmos. The multiverse becomes not speculative, but necessary. This interpretation raises staggering questions. If all possibilities exist, what does it mean to choose? If every decision spawns another world, are we unique or are we echoes, one branch among countless others? Philosophically, this vision is haunting. It gives us infinity, but at the cost of singularity. It offers certainty. The wave function never collapses, but at the price of individuality. Wave theory. In his model, particles always have definite positions, guided by an underlying wave that determines their paths. This restored determinism without collapse, though at the cost of introducing non-locality. Bohm's theory is mathematically consistent with quantum mechanics, but adds layers of reality beneath the veil. Here, uncertainty is not fundamental. It is ignorance. The veil conceals not probability, but order. Though less popular, Bohm's vision persists, a reminder that quantum mechanics does not dictate one philosophy. The veil, Copenhagen, or Bohmian mechanics, all produce the same predictions. The veil remains unpierced. Quantum. Computers and tests of decoherence may someday provide hints. But for now, interpretations are philosophical, mirrors of our deepest fears and desires. Do we crave certainty? Do we embrace infinity? Do we accept mystery? The emotional landscape. Each interpretation reshapes our relationship with reality. Copenhagen. The world is incomplete until observed. Reality is participatory. Hidden variables. The world is complete but hidden. Reality is ordered if unseen. Many worlds. The world is complete but infinite. Reality is all possibilities at once. Each vision is unsettling. Each lifts the veil slightly, only to reveal new shadows. The veil multiplies. What lies beneath the quantum veil may not be one truth. It may be layers of possibility, branching or hidden, visible or concealed. The veil does not simply cover each. We walk a path, uncertain of whether it is the only one or just one branch among countless others. Quantum fields, the indivisible points, like atoms of Democritus, billiard balls colliding in the void. Even after quantum mechanics, the language of particles remained: photons, electrons, protons. Yet beneath the veil, this picture falters. The deeper truth is that particles are not fundamental. They are ripples in underlying seas. What we call a photon is a vibration of the electromagnetic field. What we call an electron is an excitation of the electron field. Reality is not made of things, but of fields. This is the vision of quantum field theory, QFT, the most successful framework in science, where matter and forces alike arise from invisible fabrics stretched across space-time. The veil is not woven of particles. It is woven of waves. The quantum field. A field is a value assigned to every point in space. Imagine an invisible fabric, taut and omnipresent, filling all of reality. In quantum field theory, every type of particle corresponds to its own field. The electron field permeates the cosmos. The photon field too. Quarks, neutrinos, gluons, each with its own hidden sea. Particles are simply excitations, ripples in these fields, like waves on an ocean. Smash two particles together, and you are disturbing the fields, exchanging quanta of vibration. Beneath every atom, every force, every interaction, lies the invisible undulation of fields. The veil is not emptiness. It is fabric. The Higgs field, mass from the invisible. One field stands apart, the Higgs field. Without it, particles would be massless, flying at the speed of light, never binding into atoms or stars. In 1964, Peter Higgs and others proposed that space itself is filled with this invisible field. As particles move through it, they acquire mass. Like swimmers moving through molasses, slowed by their interaction with the medium. In 2012, the Large Hadron Collider confirmed the Higgs boson, the ripple of this field. It was a triumph, proving that mass itself is not fundamental but emergent, born from interaction with an invisible veil. The solidity of the world, the weight of your body, the pull of Earth, the stability of stars, all rest on the unseen presence of the Higgs field. Fields and forces. Forces, too, are fields. Electromagnetism is carried by the photon field. The strong nuclear force by gluons. The weak force by W and Z bosons. Gravity, though not yet reconciled with quantum theory, is suspected to emerge from a graviton field. Thus, every interaction is the trembling of fields. Every attraction, the exchange of quanta. The cosmos is not a machine of gears, but a symphony of vibrations, each field resonating with the others. The vacuum as field. Even in apparent emptiness, fields persist. They cannot be switched off. The quantum vacuum is their ground state, restless with zero-point energy. Virtual particles arise from field fluctuations, blink in and out, shaping reality. This picture reframes the void. It is not absence, but a plenum of fields, always humming, always alive. The Standard Model, a tapestry of fields. Together, the known fields form the Standard Model of particle physics, the most accurate theory ever devised. It describes quarks, leptons, and force carriers, all as field excitations. Its predictions match experiment to astonishing precision, sometimes to 10 decimal places. Yet the Standard Model is incomplete. It omits gravity. It cannot explain dark matter, dark energy, or the imbalance of matter and antimatter. The veil of fields is powerful, but partial. Beneath it may lie deeper fabrics still. The music of reality. Fields invite a metaphor of music. Particles are notes, transient excitations. Fields are the instruments, vast and continuous. The universe is the symphony, resonating across space-time. This is more than poetry. It is physics. The equations of QFT are written in harmonics, Fourier modes, vibrations across invisible string. Reality is music, though the notes are not sound but quantum oscillations. beyond the known fields. Some physicists suspect more fields await discovery. A field for dark matter, yet undetected. A scalar field driving inflation, expanding the infant universe. Perhaps even exotic fields we cannot yet imagine, vibrating at energies beyond our reach. If so, the veil conceals not just the fields we know, but others that shape the cosmos. The true fabric may be far richer than our current map. Philosophical reverberations. The shift from particles to fields reshapes philosophy. We imagine ourselves as made of things, atoms, molecules, matter. But beneath the veil, we are patterns in fields, excitations in invisible fabric. Identity itself dissolves. You are not matter. You are vibration. And if the fields themselves are not ultimate, but emergent from deeper laws, strings, loops, holograms, then even this vision is provisional. The veil may conceal beneath itself another veil, and another. The living veil. Quantum fields are not background scenery. They are the play itself. The vacuum is not empty stage, but restless chorus. The veil is not illusion, but the deepest substance we have found. To see reality as fields is to see the universe as one continuous ocean, endlessly rippling, endlessly creating. Every breath lies the same fabric, humming in silence, unseen but omnipresent. Particle colliders and quantum experiments, smashing the veil, the urge to see beneath. From the moment humanity first glimpsed the strangeness of the quantum world, the desire to peel the veil grew irresistible. What if particles are ripples in fields? How can we disturb those fields enough to reveal their hidden rules? The answer was simple, but colossal. Build machines that collide matter at unimaginable energies, recreating conditions of the early universe. In the instant of collision, fields vibrate violently, particles dissolve into pure energy, and the veil flickers, revealing its hidden threads. The first colliders, cracking the atom. In the early 20th century, experiments began with crude tools. Ernest Rutherford, in 1911, bombarded thin gold foil with alpha particles and revealed the atomic nucleus. The atom was not indivisible. It had structure. The veil had thinned. By mid-century, cyclotrons and synchrotrons hurled protons and electrons to near light speed. Collisions revealed new particles, muons, pions, kaons. The so-called particle zoo grew, a bewildering menagerie hinting at deeper order. It was as if beneath the veil lay not clarity, but proliferation, a kaleidoscope of forms waiting to be classified. The rise of the standard model. Through colliders, order slowly emerged. Quarks were discovered as the building blocks of hadrons. Gluons were identified as carriers of the strong force. The W and Z bosons were captured, proof of the weak interaction's hidden unity with electromagnetism. Each discovery was a note in the composition of the standard model, the great tapestry of quantum fields. The veil gave way to glimpses of symmetry, forces uniting, particles forming patterns, but mysteries remained. The Higgs boson, the particle of mass, was theorized but unseen. Dark matter and dark energy loomed beyond reach. Gravity resisted quantization. The veil still concealed its deepest laws. The Large Hadron Collider, the crown jewel. In 2008, the Large Hadron Collider, LHC, came to life beneath the French-Swiss border, a 27-kilometer ring where protons race at 99.9999999% the speed of light, colliding with energies never before achieved on Earth. In 2012, the LHC revealed the Higgs boson, the long-sought ripple of the Higgs field. It was a triumph, confirming that mass itself is emergent, born from interaction with an invisible veil. Humanity had reached into emptiness and pulled forth the weight of existence. Yet the LHC also deepened the mystery. Supersymmetric particles, predicted by many theories, remained absent. Dark matter eluded capture. The veil yielded one jewel, but held back the rest of its secrets. Quantum optics, the double-slit experiment. Not all experiments require titanic machines. Some reveal the veil with the simplest apparatus, 2 slits and a beam of light. The double-slit experiment, first performed in the early 1800s, showed light behaving as a wave, creating interference patterns. Later, with electrons, it showed particles doing the same. But when observed, the interference collapsed, as if reality itself altered under watch. Even today, the double-slit experiment is the purest glimpse of the veil. It shows, with haunting clarity, that beneath appearances, reality is probability. The universe behaves differently when no one looks. Quantum computers, harnessing the veil. While colliders smash reality apart, quantum computers attempt to weave with it. By exploiting superposition and entanglement, quantum bits, qubits, can perform calculations across vast landscapes of possibilities simultaneously. Though primitive today, these machines are the first attempt not just to observe the veil, but to use it. If successful, they could solve problems classical computers cannot, simulate the fabric of chemistry, and perhaps reveal new laws of physics. The veil is no longer merely an obstacle. It is becoming a tool. The limits of smashing. Yet even the LHC has boundaries. To probe the Planck scale, where quantum gravity resides, would require energies far beyond Earth's reach, a collider the size of galaxies. Humanity may never smash the veil deeply enough to see its final threads. This forces a humbler approach, to combine smashing with listening. Gravitational wave detectors, neutrino observatories, and cosmic surveys all extend our reach without brute force. The veil may yield not to collision, but to patience. Philosophical reflections. Particle colliders and quantum experiments are not just tools of science. They are metaphors for the human spirit. To smash particles is to smash assumptions. To peer into slits is to peer into mystery. To harness qubits is to harness ambiguity. The veil resists, but we persist. Our machines are not only instruments of knowledge, they are declarations of desire. The desire to see, to know, to cross horizons we cannot reach, the living veil. Every collider, every experiment confirms the same truth. The veil is not thin fabric, easily torn. It is thick, layered, alive. Smash it, and it multiplies. Observe it, and it changes. Harness it, and it reveals power. What is beneath is not clarity, but depth. The veil is not obstacle, but reality itself. Horizons of quantum gravity, where space-time trembles, the rift between theories. By the mid-20th century, physics had 2 towering achievements. On one side stood Einstein's general relativity, a theory of the cosmos, where space-time bends and curves under the weight of mass and energy, weaving galaxies, stars, and black holes into a grand, elegant geometry. On the other side stood quantum mechanics, a theory of the very small, where uncertainty, superposition, and entanglement reign, governing atoms and particles in a probabilistic dance. Both theories work. Both predict with uncanny accuracy. But together, relativity is continuous, smooth, geometric. Quantum mechanics is discrete, jittering, statistical. Gravity, in Einstein's equations, is the curvature of space-time itself. But when forced into quantum form, space-time breaks into infinities, chaos, paradox. Here lies one of science's greatest mysteries. What lies beneath the veil when gravity itself is quantized? The quantum horizon of black holes. Black holes are where relativity and quantum mechanics collide most violently. According to relativity, nothing escapes a black hole. Its event horizon is the ultimate boundary. But in the 1970s, Stephen Hawking combined relativity with quantum fields and made a shocking discovery. Black holes radiate. This Hawking radiation arises from the quantum vacuum itself, where particle pairs flicker at the horizon. One falls in, the other escapes. Over time, the black hole evaporates. But this creates the infamous information paradox. If matter falls into a black hole and evaporates away as random radiation, what happens to the information it carried? Quantum mechanics insists information cannot be destroyed. Relativity seems to disagree with the consistency of physical law itself. The Planck scale, where space-time foams. At scales of 10 to the negative 35th meters, the Planck length, space-time is predicted to become turbulent. Quantum fluctuations ripple through geometry, bending, twisting, tearing. This quantum foam, envisioned by John Wheeler, suggests that smooth space-time is an illusion, a coarse-grained approximation of a deeper, discrete structure. At this horizon, the veil is not matter, but space-time itself. Reality's very stage is woven from unseen threads, and beneath them may lie the theory that unites quantum mechanics with gravity. String theory, vibrations beneath the veil. One vision proposes that beneath particles and fields lie strings, tiny, one-dimensional loops vibrating at different frequencies. Each mode of vibration corresponds to a particle, photon, electron, quark. Most importantly, string theory naturally includes the graviton, a quantum of gravity. In this view, gravity is not alien to quantum mechanics, but born from the same fabric of vibrations. But string theory demands extra dimension, hidden spaces, curled so small they elude detection. If true, the veil is not two-dimensional, but multidimensional. A hidden architecture supporting reality. Loop quantum gravity, atoms of spacetime. Another vision proposes that spacetime itself is quantized, composed of indivisible units. In loop quantum gravity, space is woven from finite loops, like a network of threads. Geometry is granular, not continuous. Time ticks in discrete steps, not flow. Here, the veil conceals not waves, but atoms of spacetime, as real as atoms of matter. If correct, infinity itself is an illusion, replaced by finite quanta that prevent singularities, dissolve black holes, and tame the Big Bang. Holography and the edge of reality. The holographic principle offers yet another horizon. Inspired by black hole entropy, it suggests that the information of a volume is encoded not within, but on its boundary. In this vision, the universe is a hologram, its three-dimensional reality a projection from a two-dimensional surface. Quantum gravity here is not the unification of fields, but the recognition that reality itself is encoded on horizons. Beneath the veil lies not volume, but surface, not substance, but information, experimental glimpses. Testing quantum gravity is daunting. The Planck scale is far beyond collider energies, yet indirect glimpses appear. Gravitational wave detectors, like LIGO, may someday reveal echoes of quantum spacetime in the aftermath of black hole mergers. Cosmic microwave background surveys may capture imprints of primordial fluctuations, hints of inflation's quantum origin. high-energy cosmic rays, gamma-ray bursts, or deviations in light's travel may betray discreteness in spacetime. Each observation is a potential pinprick in the veil, the philosophical horizon. Quantum gravity is more than physics. It is philosophy written in mathematics. It forces us to ask, is spacetime real or emergent? Is geometry fundamental or an illusion of deeper information? Is the universe continuous or digital? The veil here is not only mysterious, but profound. It challenges the very stage of existence. We are not actors upon space-time. We may be ripples within it, or projections from its edge. The trembling veil. The horizon of quantum gravity is the most daunting of all. It is where our two greatest theories, both brilliant and beautiful, collapse into paradox. It is the reminder that beneath even our deepest laws lies a veil yet unpierced. And yet it is also a horizon of wonder. For in black holes, in the Big Bang, in the trembling of spacetime, the universe whispers its final secrets. The veil trembles, and through its tremor, we glimpse the possibility of unity, a single law that binds the cosmos from smallest particle to largest galaxy. Consciousness and the quantum question, the observer's veil, the puzzle of the observer. Quantum mechanics works. Its predictions shape our technology. Its equations define our understanding of matter and light. And yet, at its heart, lies a riddle unresolved. Why does observation matter? The wave function evolves smoothly, describing probabilities of all possible outcomes. But when measured, it collapses into one reality. Why should the act of looking change the state of the world? Why should an observer, a being of matter and neurons, matter at all? This enigma opens a new horizon, the link between the quantum veil and consciousness, the role of measurement. In the Copenhagen interpretation, measurement plays a central role. An electron exists in superposition until observed, when its position becomes definite. But what counts as an observation? Does any interaction with the environment collapse the wave function? Or must a conscious mind intervene? This ambiguity unsettled even the founders. John von Neumann argued that measurement chains extend until consciousness breaks them. Eugene Wigner speculated that mind itself was essential to collapse. Was consciousness not just participant, but fundamental? Was the veil entangled not only with matter, but with mind, the cat, and the observer? Schrödinger's cat embodies this strangeness. Is the cat both alive and dead until observed by a human? Or is the cat itself an observer, collapsing its own state? Where does the veil end and awareness begin? The paradox blurs categories. Perhaps there is no clear line. Perhaps the veil between superposition and collapse mirrors the veil between object and subject. Quantum mind. Theories. Some scientists dared to propose explicit connections. Roger Penrose suggested that consciousness arises from quantum processes in the brain, collapsing wave functions through gravitational effects. Stuart Hameroff extended this with the OR theory, locating quantum activity in microtubules within neurons. These ideas remain controversial, speculative, largely unproven. Yet they reveal a deeper hunger to link the mystery of the quantum veil with the mystery of the self. Decoherence, a partial answer. Modern physics offers a different view. Decoherence explains how quantum superpositions, when entangled with the environment, lose their interference. A particle observed by air molecules, photons, or dust effectively collapses without conscious observers. In this vision, consciousness is not required. Collapse is not magic, but the result of entanglement with vast environments. The veil dissolves into classical reality, not because we look, but because the world itself is noisy. And yet, decoherence does not solve everything. It explains how superpositions fade, but not why one outcome is chosen. The measurement problem remains, lurking like a shadow, the mirror of mind. Even without requiring collapse, the quantum veil mirrors consciousness. Both defy clarity. Both resist reduction. The mind is not fully mapped by neurons, just as particles are not fully described by positions. Both are emergent, mysterious, layered. Perhaps the connection is not direct, but metaphorical. The veil of quantum mechanics and the veil of mind remind us of the same truth. That reality, inner or outer, is deeper than appearances. The participatory universe. Physicist John Archibald, he imagined a cosmic-scale delayed choice experiment where choices made now influence what paths photons took billions of years ago. In Wheeler's vision, the universe does not exist in full until observed. The veil is not background but dialogue between cosmos and consciousness, question and answer, the philosophical horizon. The link between mind and quantum mechanics provokes more philosophy than physics. Is consciousness fundamental, woven into the fabric of the cosmos, or is it emergent, a byproduct of complex matter? Does the veil collapse because we look, or do we look because the veil has already collapsed? Science does not yet know. Perhaps it never will. But in this horizon of uncertainty, wonder deepens. For to explore beneath the quantum veil is also to explore beneath the veil of the self, the observer's veil. In the end, the quantum question of consciousness may not be about equations at all. It may be about humility. The observer is not outside reality, but inside it. We are both subject and object, both experimenter and experiment. The veil does not merely separate us from the world. It runs through us, shaping our perceptions, our awareness, our very existence. To ask what lies beneath the quantum veil is also to ask what lies beneath the veil of mind. And perhaps both veils are the same. What lies beneath? The final meditation? The gathering of shadows. Across the journey of science, we have pulled back veil after veil. We shattered Newton's clockwork with Planck's quanta, bent reality with Einstein's relativity, blurred certainty with Heisenberg's principle. We found threads of entanglement binding particles across the cosmos, restless oceans in the quantum vacuum, hidden fabrics of fields humming beneath matter, horizons where gravity and quantum law collide, and questions of mind entangled with reality itself. And yet, for every veil lifted, another descends. Each discovery reveals not a final truth, but a deeper shadow. The quantum veil is not one layer, but many, an infinite nesting of mysteries, each concealed beneath the other. What then lies beneath? The illusion of finality. Human instinct longs for an ultimate layer, a bedrock where the veil ends and clarity reigns. We imagine final particles, final equations, final truth. But the history of physics resists such endings. Atoms once seemed final, then nuclei, then quarks. Each time, the veil tore, and beneath it lay more fabric. Perhaps there is no last veil. Perhaps reality is not foundation, but recursion. Each layer giving birth to another, like Russian dolls or fractal spiral. Infinity may not lie in the cosmos's size, but in its depth. The veil may never end. The symphony of probabilities. If particles are ripples in fields, if fields are woven into space-time, and if space-time itself may be emergent from information, then what is reality? Not objects, not things, but relationships, patterns, vibrations, probabilities. This is the strange beauty of quantum theory. Reality is not substance, but possibility. The veil conceals not objects waiting to be found, but waves of potential waiting to be chosen. To exist is to collapse, to become one among many probabilities. Beneath the veil lies not solidity, but song, the unity of forces. The search for what lies beneath is also a search for unity. Gravity, electromagnetism, strong and weak forces, all may be facets of a single law. String theory, loop quantum gravity, holography. Each is a different attempt to glimpse unity beneath fragmentation. Whether the veil conceals vibrating strings, discrete loops, or two-dimensional codes, the dream is the same. That the cosmos, in its vastness and complexity, is ultimately one fabric. Perhaps the veil itself is unity. It is the reminder that multiplicity flows from oneness, that every particle, every galaxy, every mind is part of the same hidden whole. The question of consciousness. And yet, the veil does not end at physics. It extends inward, into the mystery of mind. The observer is never absent. Consciousness touches the quantum, even if only as question. Do we collapse wave functions? Or are we collapsed by them? Does the veil conceal not only laws, but awareness itself? Some propose that mind is emergent from matter. Others whisper that mind is fundamental, that consciousness and cosmos are coextensive. Whatever the answer, the veil runs through us as much as around us. To ask what lies beneath is to ask who we are. The veil as horizon. In the end, the veil is not obstacle, but horizon. It is the line where knowledge ends and mystery begins. It is not meant to be destroyed, but approached. Each generation pushes the horizon outward, only to find another. Horizons are not failures. They are invitations. They remind us that reality is larger than thought, deeper than theory, stranger than imagination. To live beneath the veil is to live in wonder, the poetic truth. So what lies beneath the quantum veil? Beneath certainty lies uncertainty. Beneath separateness lies entanglement. Beneath emptiness lies energy. Beneath matter lies fields. Beneath fields may lie information. Beneath information may lie awareness. And beneath all of this, perhaps nothing at all. A silence too vast to name. The veil does not answer. It asks. It beckons us to lean closer, to listen deeper, to accept that truth is not possession but pursuit. The final reflection. The quantum veil is not simply science. It is metaphor, mirror, meditation. It tells us that the world is not as it seems, that our senses are shallow, that our minds touch only the surface of an abyss. It reminds us that humility is wisdom, that wonder is knowledge, that mystery is not weakness, but strength. What lies beneath the veil may never be known. But perhaps that is the point. For the veil itself, shimmering, trembling, unbroken, is the beauty of existence. To live is to live beneath it. To seek is to walk toward it. To wonder is to already be within it.